All right, welcome to the last part of chapter 1, where we are still talking about functions and graphs, but this time we'll be focusing on transformations, compositions, and inverses. So to start with, graphical transformations, that is shifting horizontally and vertically, also called translations if you remember from geometry. And then we have reflections, we can do that also horizontally and vertically. And finally, stretching and shrinking also horizontally and vertically. So essentially we're looking at what can I do to a function in order to change its shape, to modify it. And then we'll be looking at combining functions. So what happens if I take two functions and add them together, or what happens if I multiply them, things like that. And then we'll be looking at implicitly defined functions, which basically means solve for y, and then inverses. And we might not get to the inverse part today. Okay, so why do we care? Because studying transformations will help you understand the relationships between graphs that have similarities but are not exactly the same. And most of the functions that you will encounter in calculus and in real life can be created by combining and modifying the basic functions. So they're probably not going to be the basic functions themselves, but some combination or adjustment of them. So let's look at graphical transformations. I know this is a lot of information for one slide, but I like having it all together so that you can compare what's happening for each of the transformations. So to start with, we're going to use our example as the x cubed function. The reason I like the x cubed function is because it's easy to tell if it's shifted or reflected from any direction. And for example, a parabola is hard to tell when you reflect it because it might end up being the same shape. So that's why I like to use the x cubed function for this example. So the first thing we're going to look at is if I have a parent function, f of x, and I'm doing transformations, what that looks like algebraically is I will have factors, so multiplying by something, and also sums or differences. And so within that function, I can write it, and we'll see an example on the next slide, as a combination of functions, really. So if we're looking at the variable a, notice a is out front of my function. It's multiplying the whole function. The whole f of x gets multiplied by a. And so that is a vertical multiplier. Vertical multiplier because it's outside of f of x. Everything that happens outside of essentially that function itself is going to affect the graph vertically. So if I multiply something vertically, I take it and think about like silly putty or slime. I stretch it out. And so when I stretch it vertically, it is going to get skinnier. And so a vertical stretch is very similar to a horizontal shrink. So we'll see that in the next example as well. Which means that dividing by a number or multiplying by a fraction will do the opposite effect. So instead of stretching something out, think about compressing it together or like squishing it together. And that is what we call a shrink. So our second example here is a vertical shrink, where we take our blue graph and kind of think about squishing it together. And so because it's infinite, we don't just end up with a smaller shape. What we end up with is something that looks like it got wider. So a vertical shrink looks very similar to a horizontal stretch. And what we can see is that if we're looking at the multiplying factor, so when we multiplied the whole function by 5, it stretched taller. And when we multiply by a factor inside of our function, so f of 2x or f of 5x, what happens is we can actually evaluate and simplify that function following order of operations, and a horizontal shrink is the same as a vertical stretch. They end up being exactly mathematically the same. So how can I tell when it's going to be a horizontal stretch versus a horizontal shrink? Well, the first step is to notice that my factor b is inside of the function, f of something times x. So it's multiplied by x, and what that looks like in a cubic function is that the 2 is inside of the parentheses that are being cubed. So the 2 is being cubed as well. And so how do we tell that it's a shrink versus a stretch? Well, it has the opposite rules for vertical. So a vertical number that was big, stretched, number that was a fraction became a shrink. For horizontal, if it's a big number, bigger than 1, it becomes a horizontal shrink, which is the same as a vertical stretch. And that means if I multiply by a fraction inside of my function, that will be a horizontal stretch, which is the same as a vertical shrink. Okay, so the way I like to think about it, anything that's happening inside of the function happens backwards. If I multiply by a number inside of my function, the graph shrinks. If I divide by a number inside of my function or multiply by a fraction, that graph will stretch. Okay, and everything that happens inside of the function is a horizontal transformation. Okay, I'm gonna go through that kind of introduction that I did about the shortcut of thinking about horizontal versus vertical in the next slide as well. So I'll repeat that. If we look at our variable c is inside of our function, and therefore we can think about it as being a horizontal transformation. It is added, not multiplied, but added, and therefore it is a horizontal shift. And so if you look at the graph here, the horizontal shift goes to the right and to the left. How do I know if I'll be going right or left? Well, it's inside of the function, so remember that means it moves backwards. And so if I'm going to the right, if I'm going in the positive direction, it's going to be subtraction. If I'm going to the left or in the negative direction, it will be addition. So if I have something added within my function inside of those parentheses, that is going to be, if it's added, it goes to the left. If it's subtracted, it goes to the right. Remember, inside of the parentheses works backwards. Our last variable here is d. d is added outside of the function. And since it's added outside of the function, outside of f of x, that is going to be vertical. Because it's addition, it's a vertical shift. And so if we look here at our vertical shifts, we can see that if my green example, x cubed plus 3 goes up, x cubed minus 3 goes down. So just like before, if it's outside of the function, it behaves how we would normally expect. If it's inside of the function, it behaves backwards. If you're looking at these images, the blue is always the original x cubed function, and then the equation in the color matches the graph in that same color. So how do we remember all of these transformations? Well, here's a more solid example with numbers instead of variables. I'm still going to use x cubed as the parent function. So we'll look at y equals 3 times the quantity of 1/2 times x plus 2 cubed minus 5. There's a lot of parentheses in there, so make sure you copy that down carefully. And then I'm going to compare these to our values that we were looking at. So a is 3, b is 1/2, c is 2, and d is -5. So the parent function, that is which of those main functions that we already looked at. So remember those 10 functions that we looked at in class. So the parent function is x cubed, because if I strip away all of the transformations, what's left is the cubed. That's our big function that's happening. That determines the shape of the function. This is going to be an x cubed shape, so I know it will look like this. And then we look at these transformations in the order of operations. So I say, if I put in a variable for x, what would be the first operation to do? And that's the +2. That is before I cube. So that's going to be a horizontal transformation because it's before the cubed. And because it's before the cubed, it's going to work backwards. So +2 means to the left. So this is left 2. And then our next operation for order of operations, after we take care of the x plus 2, our next order of operation would be times 1/2. Again, this is before the cubed, so this is going to be a horizontal transformation. times 1/2, if I think about it backwards, that's going to be a stretch. It's going to stretch twice as wide. So think about the opposite of a half is 2. So this will be a stretch twice as wide, horizontally still. Okay, and then I cube it. So from here on out, everything is vertical. So everything was horizontal, I cubed it, that was my parent function, and now we're working with vertical transformations. So the next thing I'll do is I multiply times 3, right? My next order of operations, I multiply times 3, that makes it a vertical stretch by 3. 3 times taller, which is, yes, also going to make it skinnier. Okay, and then our very last function here, or transformation here, is I'm going to add a -5. And if I'm adding -5 or subtracting by 5, that's moving it down. So still, it's after the cube, so it's vertically shifting -5, which is down. And so we end up with these 4 transformations. The first step was to move it to the left by 2. Then we made it wider by 2, so twice as wide. And then we cubed it. So now we're working with vertical functions, and that's times 3, making it 3 times as tall, and then -5, which moves it down by 5. So that's the order that you will perform those transformations. If you started with the x cubed function and you're going through those transformations to find your result, you have to do them in that order. Does it make a difference? Yes, it absolutely makes a difference. If I decided to stretch it before I shifted it, then I might end up with a completely different graph, especially if there are reflections. So, and remember, a reflection comes from multiplying by a -1. If it's a -1 where B is, so where that 1/2 is, if it was negative, then again, it's a horizontal transformation. So it's flipping side to side over the y-axis, okay? So be careful with those transformations. Make sure you're following in the same order as order of operations. Also, make sure, this is one of those areas that I've seen students struggle with in the past. Make sure that you are factoring out your B value. So if you have a B value and a C value, you have to factor out B, otherwise your transformations will be off. And as always, you can double check your final solution with your calculator. So just kind of check a few points on there, and then you should know whether you did the transformations correctly. Let's do a practice problem. So on our practice problem, we are going to be given a graph. This is not one of our parent functions, it's just f of x, so that we can practice the transformations without getting bogged down too much into what function it is. Okay, so we have a function here. It is a piecewise function, but the important thing is to follow our order of operations to find those transformations. So our first transformation is going to be, following order of operations, I need to do f of x minus 2. It's before I take the function, right? It's inside of f of x, and therefore I need to do that -2 horizontally. So if I have x minus 2, that's going to shift. -2 goes to the right because it's horizontally, right, by 2. So I take my graph, I'm going to find some points that are easy to move, and I'm going to go 1, 2 units to the right. Take this point as well. We'll take this point, and we'll take this point. And so here is our new graph. Okay, so let's do the next one. Order of operations wise, now I do f of x, and therefore I'm now going to do vertical transformations, right? So if I did the order of operations, the next step would be to do f of x. So I now can multiply it by that -1. So times -1 is going to be a vertical reflection. So that means reflecting over, if I'm flipping it vertically, then it's reflecting over the x-axis. So the -1 was outside of f of x, and so it's reflecting vertically over the x-axis. So I'm going to take all these points and reflect them over the x-axis. If you'll recall from geometry, all we're doing is counting the same distance away from the x-axis. So each of these points that I'm reflecting, I'm just going the same distance on the opposite side of the axis. And then it's going to follow that same shape. And so there's our function. There's our newest transformation. But we're not done yet. Our last transformation here is a +4 plus 4 goes up 4, because remember we already did f of x, we did the -2, and then we did f of x, so then that switches us to get only vertical transformations. So +4 up by 4, 2, 4, 2, 4, 4, and 4. So there's my final graph. The red one here is my final graph of y equals negative f of x minus 2 plus 4. Okay, so that's graphic transformations. What if I wanted to combine two different functions? So let's say I wanted to combine an x cubed and an absolute value of x together to make a kind of a hybrid graph. That is going to be not graphic transformations, but composition. So we have our sum, which is adding two functions together. Almost always, that's going to be how we make our polynomials. There are other functions that you can make from that as well. But for example, if I have an x cubed, a cubic function plus a linear function, x cubed plus x, that gives me one of our other types of polynomial functions. Okay, so when we look at the sum and difference compositions, those are just ways of building a lot of the functions that we're already familiar with. Okay, adding straight across. When we look at the product, we have to remember that products can be a little bit tricky when we have fractions or when we have exponents. So for example, here, if I have something like x cubed times x squared, and I multiply those two functions, this becomes x to the 5th. Our exponent rule says that if our bases match and we multiply, then the exponents are added together. So the product here is x to the 5th. So just be careful of all of your product rules. And then we have the quotient function, which honestly, this is one of the more, tends to be the easier composition to solve, because a lot of times it won't simplify. So you're just going to put f of x divided by g of x. You want to make sure that g of x is not 0. So I can't have x cubed divided by 0 because we can never divide by 0. But you also want to check if it simplifies. So how do we check when a quotient simplifies? You want to factor if you can, and check if you have any factors in the numerator that match the denominator. Okay, so when we're looking for simplifying fractions, we always want to see if we can factor. And then our last type of composition is function composition. So all of these, we're combining different things by addition, subtraction, multiplication, or division. This last one, function composition, is kind of like nesting dolls, where we're putting one function inside of another function. So what that looks like is something like I could have x cubed inside of x squared. What this would be is f of g of x. If f of x, that's the one on the outside, and the function on the outside here is x squared. G of x, that's the one on the inside, is x cubed. And the other way that we can write this, f of g, f of g. Sometimes we call it fog. FOG. Now, for this case, if we have x cubed and then squared, we're going to use our power to a power rule. This one is x to the 6th. So again, be careful with your rules here. Now, function composition is often a little bit hard to conceptualize because we don't commonly see functions that we put inside of each other. And so what I like to do is think of it just as a substitution. Okay, we have g of x, we're substituting g of x into f of x. So whatever g of x was gets substituted into f of x, and then simplify. So function composition is just fancy substitution. Let's look at an example. So on our next slide here, we are given f of x is x cubed and g of x is the square root of x plus 1. We want to find the compositions, but also find their domains. So remember from last class or a couple of classes ago, domain is all of our x values. We cannot divide by 0, no dividing by 0, and our other way that we have to watch, our other thing we have to watch for in the domain is underneath the square root, it has to be positive or 0, so no negatives under our square root. So I'm looking here, I don't see in f of x and g of x, we don't have any fractions. However, in g of x, we do have a square root. So let's go ahead and find the domain of g of x. So to find the domain of g of x, domain for g of x, we need the radicand, that part underneath the radical, to be non-negative. So we need x plus 1 to be greater than or equal to 0. Subtract 1 from both sides. That means that x is greater than or equal to -1. So the domain for g of x is all of the values from -1 and bigger. So that's from -1, including -1, so it's a square bracket, all the way up to infinity. That's our domain for g of x. Now the nice thing is, when we're doing our function compositions, a, b, c, and d, it's almost always just going to be that domain, whichever one is more restricted. So f of x, what's our domain for x cubed? What possible values can we put in for x? And then cube it. We can put any number in. We can cube any number. So the domain for f of x is -infinity to infinity. So when we combine these functions, we're looking at their domain being the more restricted, because if I can substitute a value into x cubed, but I can't substitute it into the square root, then I can't substitute it into f plus g. Let me demonstrate. So here we have f plus g. So I'm going to take f of x, that's x cubed, plus g of x, that's the square root of x plus 1. So let's just try a number. What if I tried 0? Well, 0 cubed is 0. 0 plus the square root of 0 plus 1 gives us 1. No problem. Okay, I'm going to go ahead and erase that for space. What if I try a different number? What if I try -5? So substituting, I have -5 cubed plus the square root of -5 plus 1. -5 cubed won't be a problem, but the problem is here, because -5 plus 1 is -4, and I can't take the square root of -4. So the problem didn't come from the x cubed function, because the domain is -infinity to infinity. The problem comes from our more restricted domain. So when you're looking for the domain of a composition function, you're going to look for the more restricted domain. The other way you can think about it is you can just say, I want to find the domain of this new function. What do I have to look for? I have to look for denominators. I don't have one, so I'm okay there, and radicals. And so you'll solve for the domain of the radical, and it will look exactly the same as solving for the domain of g of x. So our domain here will be from -1 to infinity. The same thing happens for f minus g. We have x cubed minus the square root of x plus 1. Again, we have that square root, so our domain is going to be limited. Our domain will be from -1 to infinity, including -1. So it's a square bracket on -1. And then we have f times g. So same thing, I'm just going to multiply x cubed times the square root of x plus 1. And then again, domain, I'm looking for denominators and radicals. I don't have a denominator, but that radical, that square root of square root of x plus 1, limits my domain. So my domain, again, is from -1 to infinity. And then the quotient is the one we have to be the most careful with, because this might introduce that first case of dividing by 0. Excuse me. And then when we substitute x cubed divided by the square root of x plus 1, so we do have that case. We have a variable in the denominator. My denominator cannot be 0. So if we look back at our domain, how we calculated our domain, we can no longer have that equals to 0 because our square root can't equal 0. And what that changes, if I don't have the equal to 0 anymore, it changes our bracket from a square bracket to a curved bracket. Because x plus 1 can be any non-negative number except 0. So now it just has to be positive. And so here when we write our domain, it will still be from -1 to infinity, but this time not including -1. Now the difference for part E is that I might have to do some solving steps that would restrict my domain further. So when we're finding the domain of a function, we also have to ask ourselves, did I have a fraction at any point when solving this function? Because if I had a fraction at some point when solving for it, then that denominator couldn't have been 0. And so when we're looking at f composed with g, the first thing I'm going to do is write this as f of g of x so that I can see which one's on the inside, which one's on the outside. So g is the one that I'm going to substitute in. So this is f of g of x, substituting square root of x plus 1. So that means I put x, the square root of x plus 1 anywhere there was an x for f of x. So this is something cubed. What is being cubed is the square root of x plus 1. So in this case, when I cube the square root of x plus 1, I can't simplify that. That's as simple as I can write it. And that means that my domain is still only concerned with that square root. So we'll have our same domain from the ones above. Our domain will still be from -1 to infinity with the square bracket this time, because I can cube 0. 0 cubed, no problem, that's just 0. But notice I'm asking myself the same questions every step of the way. Anytime I'm asking about domain, can I divide by 0? Is there anywhere that I have a variable in a denominator? Because that would restrict my domain. And then the second question, is there anywhere that I have a radical? Because that would restrict my domain. That gives me numbers that I can't substitute into the function without getting some sort of discrepancy, either dividing by 0 or trying to take the square root of a negative, which is not a real number. Okay, implicitly defined functions. So implicitly defined functions are when we are given an equation that might not be a function in itself, and so we want to rewrite it so that it is a function. So when you hear implicitly defined functions, what you should think of is solve for y. It means I am giving you an equation, and I want you to give me functions from that equation. And it might be just one function, but it might be more than one function. But in this example, we have x squared plus y squared equals 4, which you might recognize as the equation of a circle. Our equation for a circle is x squared plus y squared equals r squared. So if you have x squared plus y squared in an equation at all, that's going to be a conic section. We'll have a whole chapter on conic sections later, but if you took Algebra 2 honors, you should have seen conic sections maybe just briefly. So x squared plus y squared equals r squared, that is a circle. You will want to be able to recognize that equation. It's going to come up a lot throughout the year. So x squared plus y squared equals r squared. A circle is not a function, right? If I draw a circle, it does not pass the vertical line test. So how do we make a circle into a function? Well, we break it into two pieces. And how do we know the equations of those pieces? Is we're going to take the equation and solve for y. So we start with x squared plus y squared equals 4. Solving for y, I'm going to subtract x squared from both sides. And then I have y squared, so I need to take the square root of both sides. However, remember when we take the square root of both sides, we need to use a plus or minus. Why is that? Well, if I have, for example, 4 equals x squared, then I might be tempted to just say, okay, square root of both sides, 2 equals x. But is that the only value that I could have squared to get 4? No, I actually could have taken -2 and squared it. -2 squared is also 4. So the square root property says anytime there was not a square root and I'm creating the square root, right? There was no square root in our first two steps. Here is where I create this square root. I need to use the square root property, which is that plus or minus right there. And the plus or minus means there's actually two solutions here. I have the positive square root of 4 minus x squared, and I have the negative square root of 4 minus x squared. Now you actually have seen this equation before, maybe not this exact one, but this is the equation of half of a circle or a semicircle, and there has been one on your Math Excel that you completed for homework. You were determining if it was bounded or not. So you've probably typed it into your calculator. You saw that it was bounded both above and below. And now you can hopefully recognize that this is the equation of a semicircle. Half of a circle will always be bounded. Okay, so just a reminder here about the square root property, that whenever you don't have a square root and you're creating the square root, you have to do a plus or minus. So let's look at an example here. Our next example is just finding the implicitly defined function of this equation, and then use your grapher to describe the equation. I'd like you to try this. Just keep in mind, first of all, implicitly defined means solve for y. And second of all, if you use the square root property, you need to have that plus or minus. Our last topic is inverses. So first I'd like to review what an inverse relationship is. Now you should have seen inverses in Algebra 1 and Algebra 2, as well as geometry. So hopefully this is a little bit of review. However, you might not have recognized that all of those times that you were seeing it, that you were talking about inverses. So an inverse means it's the opposite. If I have the ordered pair AB, the inverse is BA. So the input becomes the output. It's kind of like undo. So if I do something in order to undo it, I do the opposite. So when we're solving equations, we use inverses all the time. If I have x plus 2 and I want to isolate x, I'll subtract 2. That's an inverse, okay? So the inverse relationship is the opposite. Now notice in this inverse relationship, by opposite, we mean x and y switch. And that is how we will algebraically and geometrically solve inverse functions. So we know that to solve a function, we do the vertical line test like we were looking at circles earlier. But in order to know if a function has an inverse function, then we also need to do a horizontal line test, because when we switch x and y, right, if I switch my x and y axes, then the sideways will now become the vertical. And so we have the vertical line test to test if a function passes the vertical line test, then it's a function. And the horizontal line test will let us know if that shape will also have an inverse function. So we'll see an example, but I'll give you an example here. If I have a parabola, for example, it passes the vertical line test, right? I know my lines aren't perfectly straight, but we know that a parabola would pass the vertical line test. So would it pass the horizontal line test? Well, we're gonna do the same thing, but sideways. And as soon as it passes through the function twice, it has failed the horizontal line test. So what does that mean? Well, it means that if I had a parabola and it fell over on its side, remember we talked about this a little bit when we were looking at our 12 main functions, that would not be a function. So while a parabola is a function, the inverse of a parabola is not a function. So the square root function has to be limited in order to make it a function. Remember, we had to get rid of one arm of our parabola in order to make this the square root function. Okay, so the horizontal line test tells us, will its inverse be a function? And so if I look at any graph, I should be able to tell if it will have an inverse function, meaning if it fell over on its side, if it reflected over the line y equals x, would it still be a function? So the word that we use to describe whether it has an inverse function is if it is one-to-one. One-to-one means one x value to one y value and one y value to one x value. There are no repeated x values, which is what makes it a function, but there are also no repeated y values, which makes it one-to-one. Okay, the domain we'll call D, the range we can call R, and then when we find the inverse, which we denote almost like an exponent of -1, it's notationally the same as an exponent of -1, but we don't say f to the -1, we say f inverse. F inverse, the domain and range switch. So the domain of my original function is the range of my inverse, and the range of my original function is the domain of my inverse. We saw that again with the square root function, but also with exponential and logarithmic functions, and we'll look more into that when we go into that chapter. Okay, so what is the definition of an inverse? If the inverse of a value gives you a, then the original function of a should give you that value back. So f inverse of b is a, if and only if f of a is b. And I can say that backwards. That's what if and only if means. I can read it both ways. I can say that f of a is b, if and only if f inverse of b is a. Notice these are those same coordinates that we were looking at earlier. B comma a is the inverse of a comma b. So switching those x and y values. So let's look at our next slide here. When we look at this algebraically, remember we're switching our coordinates. So algebraically, x and y switch. The second one should say geometrically. So if algebraically our x and y switch, geometrically we'll do the same thing. We'll switch x and y, and what that looks like is a reflection over the line y equals x. Y equals x is all of the points where x and y have the same value. So on either side of that line, we have this symmetry of x and y switching. So I did an example here. Let's look at the algebraic example first. Algebraically, to find an inverse, we switch the x and y and then solve for y. So remember those implicit functions, solving for y, that's what we're gonna do here. So we have y equals mx plus b. To find the inverse, we're going to switch x and y. So this was f of x. All of this is f inverse of x. So we switch x and y. Now we have x equals my plus b. This is a different function. Now we're going to solve for y. So subtract b from both sides, divide by m from both sides, and this is f inverse of x. What will that look like graphically? Well, graphically, we're doing the same thing. We're switching our x and y values, which looks like a reflection over the line y equals x. And so when we're reflecting over that line, we would take the point 3, 0 and change it to 0, 3. Now this graph is not perfectly square, like a piece of grid paper would be. But if you connect those 2 points, I'm going to try one more time. If you connect those 2 points perfectly, it should be perpendicular to the line of symmetry. Okay, now this graph is stretched out a little bit horizontally because our graphing calculators do that. It's a rectangular window and not a square window. So just because your graphs don't look like they're perfectly perpendicular to the line y equals x, that could be just because of your graphing calculator display. So be careful of watching for that. Okay, so here we have verifying that these points are indeed on inverse functions by verifying their coordinates switched place. So when will the coordinates look like they didn't switch place? If x and y are equal to each other, they'll be the same for both functions. So that's this -1, same x and y values. So when I switch them, they still look the same. But even if it's negative numbers, positive numbers, 0, in order to find a point on a geometric inverse, we're just switching those x and y values. So AB becomes BA. Let's look at another example here. Find the inverse algebraically. So we'll go through this together. F inverse of x for f of x. So first I'm going to rename this as x and y because I need to switch them. So I call this y equals 2x divided by x minus 1. And then I make the inverse. So this is where we switch from f of x to f inverse of x. I'm switching the x and y. So this becomes x equals 2y divided by y minus 1. Everywhere there was an x, now there is a y. Everywhere there was a y, there now is an x. Now I need to solve for y. So to solve for y, I'm going to multiply by the denominator, x times y minus 1 equals 2y. I need that y not to be in parentheses anymore, so I can isolate it. So I'll distribute xy minus x equals 2y. Now I have 2 copies of y. Just like if we were solving for a single variable, I'm going to put them on the same side of the equation. So I'll subtract xy from both sides. Negative x equals 2y minus xy. And now I have 2 copies of y. These are not really like terms because one of them has an x, so I can't really simplify. But what I can do, because the y's are on the same side of the equation, I can factor out that GCF. Now this is an important step that a lot of people tend to forget. If I have 2 copies of y, I need to put them on the same side of the equation and factor them out. So now I have negative x equals y times 2 minus x. Now I have only 1 copy of y, so I can divide by 2 minus x on both sides. Negative x divided by 2 minus x equals y. And then the last step is going to be, because it says to find f inverse of x, I'll write it in that notation. F inverse of x, just another name for y, equals negative x divided by 2 minus x. Now, if you had solved this a little bit differently, you might get a different looking equation, but it should be equivalent. So you could also have ended up with x divided by x minus 2, because that's just an equivalent way of writing the same function. So switch your x and y. That changes you from working with f of x to working with f inverse of x, and then solve for y. Find that implicit function. That new function that you found is the inverse function. Okay, one more, we're going to do this geometrically. Find the inverse of the function graphically. So the way we do this, again, just switching x and y. So in order to know if it's a function, I can test if this is a one-to-one function by checking the vertical line test. Vertical line test works. And also the horizontal line test. Horizontal line test works. Okay, and then I'm going to go ahead and erase those lines so that you can see that I'm drawing an inverse. I'm going to draw my line y equals x. Let's see. That is the mirror. That's what I'm reflecting over. But in order to find the points to reflect, I can just choose their coordinates. So this is 0, 1 is going to reflect to 1, 0. And then I'll choose another point. So this looks like 1, 2 will reflect to 2, 1. And then another point here, I have -1, 0 reflects to 0, -1. Now a point that's on my line of symmetry, my axis of symmetry, is going to stay on that axis of symmetry. So I'm kind of copying this graph. And the way you can check if you did it correctly, if you made your curves correct, is tilt your head a little bit to the right and ask yourself if it looks like when you fold it, it would fold over onto itself. Okay, so think about like if it was a stamp, if it was wet paint or something, and I folded on the line y equals x, would the paint land on my new graph? And that is how we can sketch the function of an inverse. Okay, so your practice for this is that example from the previous slide. Let me go back to that slide just so it's the last screen on here. The implicitly defined function here, that's your practice for tonight. And that will be the end of tonight's video. Email me if you have any questions.